So let's look at this problem, two functions of two random variables. So we are given x and y, we also have their joint density function. If these two are independent to start with, then the joint density function of course will be the product of the density functions, right? And you have two different functions. What we want is the joint density function of these two new random variables, z and w. So we could start with the distribution function of the z and w. Z comma w is probability of z less than z and w less than or equal to lowercase w. But z is given to be g of x plus y is less than or equal to z, and h is and w is given to be h of x y less than or equal to w. Then of course, as in the previous case, for a given, remember z and w are given, these are given specific values, right? So you go to the xy plane, find out the region where these inequalities are satisfied at the same time. So this may be the region where this is satisfied, and this is the region where, let's say, g of xy is less than or equal to c. You change the z, this region is going to become larger or smaller, or this could be a combination of few regions, etc. And this is the region h of x comma y is less than or equal to z. So we want the region where both these inequalities are satisfied. So let me call this to be dzw. So this is the region where for this specific values of, I'm sorry, this will be w here. So for this specific value of z and w, this is the region where these two inequalities are satisfied. Let's say. So it would be this region. So then naturally, of course, this would be given by remember, this is the region where x and y satisfies this inequality as well as this inequality. So what you have here, you have to imagine, is the joint distribution function of x and y. That's what we are. So we need to integrate it over this region. So that would be fxy x comma y dx dy. So I'm just going to write it as integrate over, so xy belongs to dzw. So in principle this is good, the rest is all details. You can, for example, depending on the regions, you just draw it and do it. Now what I want to discuss, so for example, if you look at the book, few problems are done in this manner. But when these are algebraic functions, then generally you also have a shortcut, which is what I want to discuss. So this is a technique very similar to what we have done in the case of one random variable. So let's look at this. The probability of this specific event where the random variable z is between z and z plus w, and w is between w and w plus lowercase w. So you have z w, and we are saying this is what we are interested in. Of course, here lives fzw, z comma w, but this is unknown. This is what we are trying to find out. Nevertheless, if this is unknown, so remember this is z plus delta z, this is w, this is w, this is w plus delta w. So if you recall, whether it is unknown or known, once this is the density function, this probability is what? Anybody in terms of that density function, what is it? Of course, this is the area under the joint density function from here to here and here to here, but this region is extremely small. So what? Remember, the density function is here. The region is very small, so finding finding this volume is the same as what? Imagine a tiny rectangle. So the area under that is what? The base into, so what is the height? FCW, right? So this will be FCW multiplied by del Z del W, right? So that is fine. So what happens is now we have to somehow translate this into the XY. This is the problem. So what is the translation? So if you look at here, if I pick up a point Z comma W, that's this point, Z comma W, I have what happens in the other region. You can see. So this is how we bring in this. So listen to me. I pick a point Z comma W. Then Z is of course G of xy because it's given. W is H of xy. So you can solve these equations. Together they may have multiple solutions. So let me give you an example. Suppose Z is x plus y, W is x minus y. Of course here you only have one solution. X1 is C plus W by 2. Y1 is C minus W by 2, right? But you can imagine if this was square or etc., there will be multiple solutions, right? So these solutions are now in this plane. So I have one solution here, x1, y1, right? So I have one point. I may have another point xn, yn, x2, y2, etc. So look at this, corresponding to each point here, you may have multiple points, right? Then what happened? Look at here, if I move the Z, listen to this, if I move Z to C plus delta Z, I have another point here, right? So you can go again solve this problem. You put Z equal to C plus delta Z, but W is still this, you will get a new pair of Xi's, right? So that will be, of course, you can imagine it will be close to this, right? So there will be one point here, another point here, etc. So corresponding to 4 points here, you will get 4 points here, but they are not going to be rectangle exactly. So you may get some shape, right? In general, there may be multiple solutions. So the probability of when something belonging to in the CW domain is the same as it like before. It could be here, it could be here, it could be here in the XY plane, because all these are valid solutions, right? So bottom line is you just need to figure out how this under this transformation what is this tiny area here in terms of delta C, delta W. There's a long discussion in the book. I'm not going to reproduce all this, but bottom line is that this area is given by the Jacobian of the transformation. So first of all, before I go that, from here this much is clear. So this probability, so look at here, the probability that the random variable capital C and capital W will belong in this tiny infinitesimal region when something happens here. What happens in the xy plane is the random variables x and y, capital X and capital Y could be here or here or here or here. So we could say this is the same as, but each of this would be what? The probability of that would be fx xi comma yi multiplied by delta xi delta yi from here, right? So this is going to be fxy xi comma yi delta xi delta yi. So we are almost there. What we are looking for is this density function. So this is going to be, you bring in this infinitesimal thing and area and put it underneath this. So from here you get f of CW, C comma W is summation over all solutions fxy xi comma yi delta xi, or more importantly, this may not be delta xi delta a. This is going to be this area. I'm going to call it delta a1, delta a2, etc. But this is in terms of xi, yi. So this delta ai over delta z delta w. And this is given by the Jacobian of the transformation. So the Jacobian of the transformation, you can write it in two ways. So you can either write it in terms of the given functions dg by dx. Remember, g is in terms of x and y. dg by dy dh by dx, dh by dy. Oh, so this I'm going to, the notation I use is generally, this is the specific solution xi comma yi, because then the or you can also, if you can solve this in terms of, so you can, these two functions you can also write in terms of x1 equal to g inverse of c comma w, and yi in terms of h1 of z comma w, the inverse functions. In other words, look here, g of xy is z, h of xy is w. I'm going to express x in terms of z and w, y in terms, if you do this, then I can take the derivative with respect to z and w. So this Jacobian also could, the related Jacobian is dg1 with respect to z, dg1 with, because g1 is a function of z and w, or dh1 with respect to z and dh1 with respect to w. And this I am going to write c comma w. So the relation is, this is the inverse of this, or this is the inverse of this. So this ratio will turn out to be, look at here, this ratio will turn out to be this. So you can write it in terms, remember the ratio is a positive number, so it's the absolute value of the Jacobian. So you can write this in terms of this, in which case you put it in the numerator. But if you want to write it in Jacobian in terms of the original function, then remember I told you this Jacobian will be the inverse of this. So let me rewrite the formula here. So FCW right? So this ratio is the Jacobian, j of z comma w. That's in terms of the Jacobian expressed in terms of the derivatives with respect to z and w, or the Jacobian expressed in terms of the original x and y. So remember, this is very similar to the one function of one random variable. In that case, there you didn't have the, instead of the Jacobian, remember the formula was 1 over dy by dx, right? This is your y, dy by dx, that will be in the denominator. One function, right? Think of, you only had g, y equal to g of x. So we took the derivative with respect to y, which will be dy by dx, 1 over dy by dx, fx evaluated at xi over all solutions. So very similar. So let me, easiest thing is let me do a problem, couple of problems, right?
Yes. Yes.
So look at this. So this is a classic problem. Z is x squared plus y squared. and theta is tan inverse y over x. So this is our z, this is our w, and x and y are, so this is an example, x and y are independent, so I am going to write it like this. 0 mean Gaussian random variables with identical variance. So isn't this? Each of them is 1 over square root of 2 pi sigma squared e raised to minus x squared over 2 sigma squared multiplied by y squared over 2 sigma squared. So this is that's where we are going to start. You understand the problem? X, y, 0 mean independent Gaussian random variable or normal random variable with equal variance. Sigma squared. So what is this quantity? Anybody remembers what this is? Huh? What did you say, circle? This is magnitude of from the two random variables. This is
the
phase, right? Because the idea is if you think of this, you can write this as, right? So that's the relation to z is of course magnitude. And you already know what is the distribution of this? Anyone remembers anything? Rayleigh, not Cauchy, Rayleigh. We proved that this is Rayleigh. And this one? I don't know whether you remember. If x and y are independent Gaussian with equal variance, what is the density function of y over x? Anyone? We did this last time, y over x. Cauchy. Y over x is Cauchy. Look here. Now, a couple of weeks back we did, if something is Cauchy, tan inverse of Cauchy is?
Still Cauchy.
No. Anybody remembers? I think I even did this last week. Huh?
Still Cauchy.
1 over that is Cauchy. You're confusing with. What we have shown is if z is Cauchy, 1 over z is Cauchy. But what about tan inverse of w? W is Cauchy. This is Cauchy, I agree. We did this last week. So look at here. Huh? Very good, uniform, right? So we know this is actually, or even now we know this is uniform. This is Rayleigh from last week. But what we do not know is their joint density function. So a lot of questions will be there. You have two random variables. What are the two possibilities between these two random variables? Anyone? They could be what? I mean, when you have two random variables, what are the possibilities? They are either independent or dependent. So what do you guess between these two? Dependent or independent? I am talking about z and theta. They are dependent or independent? Look, what did you say?
Dependent.
Because of what? You are saying these two are dependent. He is using literally because he looks at the board and he sees that z depends on x and y and theta depends on x and y. So your natural conclusion will be what? If something depends on the same thing, these two are dependent, right? So you may be right, you may be wrong, we will see. So these are if you have two random variables, these are the type of questions. We want their joint density function, we want their marginals, then we want to determine whether, actually marginals you already know, but then we want to know whether they are dependent or independent. So we have z equal to square root of x squared plus y squared, and you have y over x to be tan of theta, right? So from here y is x tan theta, right? So you plug it in here, y equal to x tan theta, x goes out. What do you get for x? Anyone? Huh? Right, or x equal to z multiplied by? Alright, so that you can see literally also x equal to z. He says this is one solution. And how about y?
Z sin theta.
I mean, you don't have to guess, you plug it in here. X is c, so this is sin theta over cos theta, x is z cos theta cancels, so you get y z equal to y sin theta. Now, if you restrict theta to be so if you you also have another set of solutions where you can put minus, but it all depends on the value of theta. So we will see what range it works out here, because tan theta goes like this, right? This is the principal value goes from minus pi by 2, right? So this is tan theta. Principal value goes from minus pi by 2 to pi by 2, but you can also take multiples of that. So you see this is your one solution, right? Look at here, suddenly I have been able to express the for a given c and the theta was given to be a tan inverse of y over x. So I have been able to express x in terms of, look at here, that's what I meant, look at here. I have been able to express x in terms of z and w, y in terms of z and w. Instead of w we have theta here. So this is my x1, y1. We can also bring in the other solution which will be minus z cos theta, because that also satisfies this, right? x2 equal to minus z cos theta and y2 equal to minus z sin theta. Why is that? Because take x2 squared plus y2 squared, you will get this same z, right? Take the ratio, you will get the same theta. So two solutions. Okay. All right, let's find the Jacobian. Either formula you can use. Now since we have this, so this is your g1. X has been expressed, so this is your g1 function. This is your g1 of z comma theta. This is your h1 of z comma theta. So if I take the derivative of the Jacobian with respect to, so that is what, dg1. So the derivative, look at this, derivative of this with respect to z, what do you get? So right, so that's going to be cos theta, right? Derivative of g1 with respect to theta, what do you get? g1 is z cos theta, so minus z sin theta. Derivative of h1 with respect to z, what is it? Hello, h1 is here. With respect to z would be what? Anyone? Why is this hard now? This is c sin theta. So what is its derivative? Remember, this is z sin theta. The derivative with respect to z is what? Sin theta, right? So this is, and the other one here? Derivative of all right, so what's the determinant? Jacobian is the determinant of this 2 by 2 matrix. So that's going to be z itself, right? So we have everything that we need. So fz comma w is going to be literally here. I have two solutions. The Jacobian is z in both the case, because you see whether I put the this set or this set, you will get exactly the same value. So it's going to be z fxy x1 comma y1 plus z fxy x2 comma y2, right? Right?
Yes.
And you can see when you substitute, what do you get? So this c over 2 pi sigma squared e raised to minus x1, so what is it? So here you put x1, here you put x1, y1. x1 squared plus y1 squared is how much? C squared, right? x2 squared plus y squared? Also c squared. So the second term is exactly the same as the first term, right?
Yes.
So you see this is going to be c squared over 2 sigma squared, right? And z is? C takes what values? Look at again. C is square root of x squared plus y squared. That's the magnitude. So z is positive, right? First of all, this is this term evaluated. You evaluate this term, you get the same thing. So I get a 2 here, right? 2 cancels. So I get 1 over z over pi sigma squared e raised to minus z squared over 2 sigma squared. Z is positive, and theta, the principal value, goes from minus pi by 2 to plus pi by 2. So let's find, even though you know the answer, let's find out FCC. FCC is going to be Fc comma theta. Instead of W, I should write here theta. Fc comma theta. What should I integrate? Anybody? To find out FCC? D theta. Theta goes from minus pi by 2 to pi by 2. And f theta would be, I should integrate out what? Anyone? Z goes from where to where? Yeah, 0 to infinity. So let's substitute, and so this is minus pi by 2 to pi by 2. The answer here is z over pi sigma squared e raised to minus z squared over 2 sigma squared d theta. I don't see any of the d theta, so this whole thing goes outside. What is the value of the integral? Anybody? Hold on. This whole thing, see, this is independent of theta, so that goes outside. So the integral is simply d theta. Top limit minus bottom limit. What do you get? Pi. Pi cancels. So do you see that the answer is z over sigma squared e raised to minus z squared over 2 sigma squared for z positive, right? What is this one? Rayleigh, which we had it before. And here, so 0 to infinity z over pi sigma squared e raised to minus z squared over 2 sigma squared dz. So easiest thing is you put this equal to u. So u I am going to substitute as z squared over 2 sigma squared. So this means du is 2z dz over, look at it, 2 sigma squared, 2 cancels. So you get du is z dc over sigma squared. Look at here, z dc over sigma squared. So can't I write this as 1 over pi integral 0 to infinity e raised to minus u du, right? 1 over pi goes outside. Z dc is z dc over sigma squared is du. What is the area under, what is this integral? Integral 0 to infinity e raised to minus u du. Huh? This? 1. So you get the answer to be 1 over pi. What is that density function? Uniform. So density function of theta is uniform, and density function of z is Rayleigh. And moreover, in this peculiar case, look at this. I see that just after doing all this, I see that If I multiply this two, you get back this, right? Because this I can write it as 1 over pi here. This is the uniform, this is the Rayleigh. So what do we conclude here? What do we conclude? That you are wrong. They are independent. So there are always surprises, so don't be judgmental just by seeing a person. Same thing here, right? Don't be judgmental by seeing a problem, right? So z and theta are independent. See, this doesn't make any sense in the if you use common sense, but it is true. Now, so let me summarize what is true and what is not true. So you have, so all the conditions are, you need to be carefully met. You need a zero mean, independent, and Gaussian random variables with equal variance. Then the magnitude and phase are independent. If any one of these conditions are violated, then he is right. So your hunch is right most of the time except this special case. So I'll do all the other cases. There are several videos on this same topic. You just need to go and listen to it. But I'll do one case for you now before we move on. Okay. So let me, for example, take them to be not equal variance. Okay. Let me see how, that's the probably the easiest case to. So one final question here is, you could say that this phase should be what? If it is phase, this should be between, it should go around the all 0 to 360 or minus pi to pi. So that's easy to fix. You this whatever is this random variable, you multiply by 2, it will still be uniform, right? So call a new phi to be 2 theta. So then of course if this is uniform, this will be uniform, except this will be 1 over 2 pi. Phi will go from, as you can see, from minus, so put the limits here, minus pi to plus pi. Or other way would have been only consider one function. So sometimes, so if you consider that random variable to have range from minus pi to pi, this will be 1 over 2 pi, and so z would be still greater than 0, and theta goes from minus pi to pi. Remember, so the argument is you define a new random variable which is 2 times the old random variable. So the new random variable has double the range. If the original one was from minus pi by 2 to plus pi by 2, here we are considering beyond the principal value. So we are considering from minus pi to pi. So the general theorem is that, or a special case is that when you have a complex Gaussian random variable which is zero mean and equal variance and independent, the magnitude and phase, whether you consider the principal value or from minus pi to pi, are independent random variables. So let me consider a generalization of this. Look at this. Here I am considering the case where they are still zero mean but not equal variance and correlated. So this is still the same problem, except the two conditions have been relaxed. They are no more independent. Rho is not 0. Remember, this is the correlation coefficient, which we will discuss soon. And so this is, I think we discussed, at least I showed you the density function. This is the general case of two jointly Gaussian random variables. You put rho equal to 0, of course x and y you can see is independent. So let's try to do the same problem here quickly. So this is done in detail, so I'm just going to summarize the results. And theta is tan inverse y over x. So you can say more or less all the steps are the same solution, the same Jacobian. So the Jacobian is still z. So the joint density function would turn out to be the Jacobian multiplied by the density function of, so the Jacobian multiplied by the density function evaluated at x1 comma y1. As I said, if I do that, then I am considering the theta to be from minus pi to pi. If I take both the solutions, it's over the principal value. Then you can multiply by 2, or let me just take care of one solution. So this is z because we had it before. So z over 2 pi sigma x sigma y 1 minus rho squared e raised to minus 1 over 2 minus rho squared. So x is, we have it before, right? X1 is what? Z cos theta, right? X1 and y1. Remember the two solutions are here, right? X1, right, everything is the same. Z cos theta, y1 is z sin theta. So let me substitute for x and y. So this is z squared cos squared theta over sigma x squared minus 2 rho z squared cos theta sin theta, right? Because xy over sigma x sigma y plus y squared sin z squared sin squared theta. Over sigma y squared. All right, now what? Now we need to find out FZC and F theta theta. It's a bigger mess, right? All right, so some you can see here, 2 sin theta cos theta is what? You can write the numerator as what? Anybody?
2 sin theta.
All right, so this is z rho c squared sin 2 theta, right? Because 2 sin theta cos theta is sin 2 theta, right? And cos squared theta, I am going to write it as what? How do you write it in terms of cos 2 theta? Cos 2 theta is what?
2 cos square theta
Minus 1. So cos squared theta is 1 plus cos 2 theta over 2, right? From here. 1 plus cos 2 theta over 2. This is also same as 1 minus 2 sin squared theta, right? So this sin squared theta is 1 minus cos 2 theta over 2. So you see z squared is common. I'm going to do some simple, not going to write all the steps. So let me call this constant since I want to as 1a, right? So this is az, right? This whole thing 1 over this thing is a constant, you can write. Then e to the power minus, look here, z squared is, I'm going to pull out, right? Because z squared is here, z squared is here. So z squared, look at here. Here I have, I'm going to do this mentally, so you just follow me, 1 over sigma x squared. Then last term 1 over sigma y squared. And there is a 2 here, 2, 2, 4. So this becomes 4 multiplied by 1 minus rho squared, right? The rest of the terms involve cos theta, etc. So this is e raised to minus, z squared is still here. So z squared over 4, 1 minus rho squared. Then you have 1 over sigma x squared minus 1 over sigma y squared multiplied by cos 2 theta minus, look at here, 2 rho sine 2 theta over sigma x sigma y. Now you probably, some of you know, see this is a, you know how to simplify this, right? This is some constant multiplied by cos 2 theta multiplied plus some other constant multiplied by sine 2 theta. So how can you write that, rewrite that as, anyone? Call this constant to be small a. So this is small a, this is small b, everything other than sine theta. Then, huh? So this is a cos 2 theta minus b sine 2 theta. Anybody? I'm going to do, this is a trick you must have seen, right? So this is what, anyone? So this you can call some cos phi, then this will be sin phi. Cos phi cos 2 theta minus sin phi sin 2 theta is what? Isn't it? Right? So you know the value of A, right? A is this, B is this. So this whole thing, this quantity within the bracket, this I can replace this whole quantity by this one, right? So the joint density function of Z and W turns out to be A Z e raised to minus. So you can see what a mess it is if you relax some of these conditions. But you see, at this point, unfortunately, we can't conclude. If there was no Z, at least you can say theta and Z are independent. But Z is there on both the terms. But now the next job is to find out the Z and then find out the theta. You know the procedure, of course, all you have to do is you take the joint density function and integrate out the theta. Theta, of course, in this case, remember, I only took one solution, so the theta goes from where to where? Anyone? Remember, once you take both the solutions, it's minus in the principal value. Otherwise, theta is unrestricted. It's over the whole minus pi to pi, right? And this will be Z is, of course, till 0 to infinity, Fz W C comma theta dc.
Sorry, why is minus pi to 2 pi?
Because as I said, in the complex random variable x plus jy, if you write it as Z e raised to j theta, theta could take any value between 0 to 360, right?
Okay, but why in the early question?
There I'm saying if you restrict to theta, remember tan inverse y, so I'm saying I'm going to only look at this region, which is the principal region.
Okay.
Then there are two solutions, and there I have restricted theta to be from minus pi by 2 to pi by 2. You multiply that random variable with the 2, you get from minus pi to pi. So the at least the finding theta is easy. So I'm just going to do that, and we will again, as I said, there is a completely, I think there are 2 other independent videos on the same topics. So you get, it's like take 1, take 2, take 3. You get 2, 3 different versions of it. Each version is, I emphasize on something else. So if you miss something else, you can see it there. So this integration is easy because remember you are integrating with respect to c. So you'll have to integrate here, and those of you know that particular integral can be expressed in terms of the Bessel function. So this integral is this constant e raised to minus z squared over, so I'm going to, this whole thing is a constant, right? 1 over sigma x squared plus 1 over sigma y squared, and divided by 4 multiplied by 1 minus rho squared. Then what you have is minus pi to pi, right, e to the power, let me call this to be b. So e raised to minus b cos 2 theta minus phi naught d theta. You can see this phi naught is not going to play any role because you are just in, if you make a simple change of variable, do you see that? This will go from minus phi minus pi minus phi naught to pi minus phi naught. In other words, the integration is over 360 degrees. So at this point, whether you write this or not, it's exactly the same. And this is the Bessel function evaluated at b. B unfortunately, look at here, b involves z squared. So I'm going to write this as z squared multiplied by a squared plus b squared over. So what is my point? My point is this multiplied by this. It's not Rayleigh. And if you, the other one is a little easier if you want to see the. So in fact we can, to do the theta, look at here, let me use this term. This is the same as, let me pull out to z squared here. So z squared goes out here, z squared is gone, z squared is gone. So if you want, this joint density function also can be written as z over 2 pi sigma x sigma y 1 minus rho squared e raised to minus z squared over so I'm going to write it as some constant. Let me call, since I used to be, let me call it to be c, where c is going to be cos squared over sigma x squared minus 2 rho minus rho sine 2 theta over sigma x sigma y plus sine squared over sigma y squared. Okay, that's your constant c. So let's take this and integrate out c. I'm sorry, z. So which is what I'm going to do here. Look here, I need to integrate out c. So that's easy because if I put this to be a new variable u, together with this I can integrate this out. So let me define c squared by 2 to be u. Look at here. So c z dc would be du, right? Because 2 cancels. So z dc will be du by c. So this integral turns out to be, let me substitute that here, 1 over 2 pi sigma x sigma y 1 minus rho squared half integral 0 to infinity e to the power minus c squared by 2 z dz, right? So I'm going to substitute this to be by u, and then this becomes du by c. So this integral now becomes 1 over 2 pi sigma x sigma y. 1 over c is a constant. The rest is what? Integral 0 to infinity e raised to minus u du, which is 1. So that's the answer. So finally let me just substitute for c. So maybe you didn't ask for this much, right? Just to show you that if you go away from the generalist, this is all you do. Almost all the books only show that a special case when the variances are equal and the random variables are independent. So look at here, this is right now you can do a couple of special cases. What is a special case? Put both the variance equal to, take the case when the random variables are independent, rho is 0. Rho is 0, this term is gone. Still the theta is not uniform. Put the sigma x and sigma y equal to sigma squared. Then what happens? Cos squared plus sin squared is 1. Sigma squared goes on the numerator, cancels with sigma squared, rho is 0, so you get 1 over 2 pi, which is uniform. So this is the general case. If you put rho equal to 0, sigma x, sigma y, so I'll finally write it here and then that should be good enough. So if rho is 0, f theta, theta is, look at there. So that is still not uniform, right? Now rho is 0, sigma x equal to sigma y. Then of course f theta, theta is 1 over 2 pi. Because these two are equal, that goes, cancels this, right? And this is what we had before. And in that case what happens is this becomes 1 because b becomes 0. Why is b 0? Because look at a and b. I don't have it here, you have it. A rho is 0, so b becomes 0, you get back Rayleigh. So what's the moral of the story? If they are jointly Gaussian, the magnitude is not Rayleigh. The phase is not uniform. And he is right in the sense the magnitude and phase are not, as he says, dependent. But there is a special case when things are against counterintuitive, okay.